Hello, everybody. How are you doing today?
Fine, Prof.
Oh, good. You look like you're in a nice sunny place. That looks nice out. Where is that? Are you in a field, Glory?
Yeah, no, Prof, it's just in the school environment
Oh,
by
okay.
our chapel. Yeah,
Okay.
Prof.
Those are some pretty trees there.
Yes, I just love the natural environment.
So, Caldrin, do you have any pictures of your car yet to show us?
I think I do actually.
You're welcome to share the screen if you want to show us what you're into these days.
Give me till Friday.
Okay, sounds good. Actually, why don't we wait till Monday, because on Friday we're going to have a guest lecture from Dr. Farusa. But so hopefully it'll be timely if we get through this next section. Has everybody got a chance to see my responses to the Planet Krypton? Those should have been posted directly on Flipgrid, on Flip. So you should have gotten an email automatically generated saying that you have a response there. If you haven't seen it, go to where you did your last flip and you should see a response, my video response. If you don't, just email me and I'll send you a direct link to it. It was just easier to upload them there and hope that the whole gizmo works correctly. But I was very, very satisfied. Everybody did a really good job on their climate calculations, coming up with the right temperature. It looks like you kind of all get it. So I was really happy to see that. Desire, when you get a chance, I'd really like to see yours as well. So if you get a chance, please try and do that Planet Krypton, because the act of going through making those calculations, remember, these are equilibrium calculations. So it's after, you impose some kind of change, or once you figure out what the energy into the planet, given so many atmospheres, you can figure out what the temperature should be at the surface after it reaches equilibrium. And so our last two lectures have been on non-equilibrium stuff. It's been on how you have transient adaptation when you have a new change in the amount of energy in or the amount of energy going out, how it takes time for the planet to adjust. and that's where we looked at the term called radiative forcing, which is basically the magnitude of the energy imbalance imposed on the system. And over time, the system will adjust by raising or lowering the temperature of the planet, so it can adapt to whatever this new energy balance is. And it takes time, right? Temperature doesn't change automatically. If you pull a turkey out of the freezer, it doesn't immediately come to room temperature. It takes a little while. At first, it warms up quickly, and as it gets closer and closer to the equilibrium temperature, it's still warming up, but not as quickly. But eventually, that energy balance is kind of wiped out. And so that gave us this term of radiative forcing, which is, how many watts per meter squared is our energy difference. And so we're going to build on that today when we're talking about climate sensitivity. And this part is a pretty big deal. Let me go ahead and, that's not the right thing. There we go. Climate sensitivity. Move this over here. And so climate sensitivity is a metric that tells you how sensitive the climate is to greenhouse gases added to the atmosphere. A high sensitivity means you get a lot of warming from just adding a small amount of CO2, whereas a low sensitivity would mean you can add a lot of CO2 and you don't get much warming, okay? And so it's really important for us as climate scientists to really understand how sensitive is our climate to increasing CO2. And there's been many articles on this. It's a major factor that people discuss when they're talking about climate change. Some say it's the most important number in climate change is this climate sensitivity. And it's slightly based on radiative forcing. And so we'll talk about this, okay? So there's many definitions for climate sensitivity, and we're going to start with one, but we'll probably evolve to a slightly different one. But the easiest to understand is it's the amount the climate will warm in response to 1 watt per meter square of radiative forcing, okay? So if you change the amount of energy by 1 watt, how much will the climate warm? And that is, we let the system run until it reaches equilibrium. And so the warming we're talking about is that equilibrium warming, once it finally reaches equilibrium and stops warming. And based on what we've talked about so far, it should be pretty easy to think about how you calculate that number. So, we've already done this calculation where we know the sun, given its the solar constant and the albedo for the planet, we've already measured that we get about 238 watts per meter square coming into the planet, and at equilibrium, that means going out of the planet as well would be 238. And when we plug this into our Stefan Boltzmann relationship and solve for temperature, we get 254. Now note here, I have 254.54. That's because for what we're going to do now, we need those extra digits of precision, okay? Because we're going to talk about small differences, but they're real, okay? And so, if we ask the question, how is the temperature going to change if you add 1 watt per meter squared, of energy, of radiative forcing? That's the difference in the energy balance. So now, instead of being 238, it's going to be 239. And so 239 coming in, once it reaches equilibrium, it'll be 239 going out. And a body generating 239 watts per meter squared would have to be at a temperature of 254.80. That gives us an increase of temperature of about 0.26 degrees Celsius. It's not very much, but we're only talking about 1 watt per meter square. And again, we're not taking into the effects of atmosphere or anything like that at this point. This is just a simple idea of how much the climate will warm in response to 1 watt per meter squared of radiative forcing. And so our first estimate is going to be it's 0.26. And this is for our 0 atmosphere layer. So we didn't have an atmosphere in this one. But that's kind of a really awkward value to use. So often, almost always, what people use nowadays when they're talking about climate sensitivity, it's the amount of warming that you would get at equilibrium when the amount of CO2 in the atmosphere doubles. Okay, so we're going to double the CO2, and then we want to know how much warming we would expect at equilibrium. And so the radiative forcing, remember that term that we had before, that's the difference in energy balance. So when you double CO2, scientists have calculated that you get a radiative forcing of about 4 watts per meter squared. Okay. And so for doubling CO2, that means you can just multiply those, right? Because we know if you go up 1 watt, you're going to increase by 0.26 degrees. So by 4 watts, you're going to go up by 1.1 Kelvin. And so this should be a plus 1.1 Kelvin. This is an important number, okay? A very important number. That's one that you should remember. It's what you would expect if you double the amount of CO2 in the atmosphere, how much warming you should get. And this is based on a number of different factors, historical data, and predicted measurements. It would be simple. Anyone have any questions on this? Does this make sense so far? We wanted to see what's the effect of adding 1 watt per meter square of energy coming in, how that would change the temperature. Scientists tell us that when you double the amount of CO2, that's a plus 4 watts per meter squared. And so we can calculate that, well, if for every watt per meter squared, it's 0.26. And so if you got 4 of those, we should expect if you doubled CO2 to get a 1.1 degree Kelvin rise or Celsius rise. But that's not all. There are feedbacks. So this part is really important because this part makes a huge difference. Because as the planet warms up, things on the planet start to change, right? We know this. And these changes can affect how the planet warms. What are some of the effects that you see when the planet warms? I'm asking you guys.
Increased glacial melting.
Increased glacial melting. Okay, that's an excellent example. So if glaciers, if you get increased melting of ice, how should that affect the energy balance for the planet? Or how could that affect the energy balance for the planet? Think of our main equation for figuring out energy in, right? It uses what? The solar constant and what else?
Boltzmann.
No, so we got
an equation. Oh,
so the no, this is for figuring out energy in. So you got the solar constant telling you how much energy is shining on the planet, but that's not the energy we use for how much is getting to the surface. We first have to factor in the what?
the atmospheres.
No, we're talking about the reflectivity, right? what's that called? The amount of reflection you get? Gloria, I think you're saying something. You're on mute, so we can't hear you. I think you're on mute.
Albinos, Prof. The albino.
Yes, the albedo, right? And
The
so, yeah, right. So
yes.
this is what we call the ice albedo feedback. You have some initial radiative forcing. It can be the increase in CO2. Doesn't really matter what it is, but that causes an increase in temperature, right? And just as Caldry had mentioned, when the temperature increases, the ice melts. When the ice melts, as Glory mentioned, that's going to decrease the albedo because usually the ice is nice and white and shiny, so it reflects that visible light back off the surface and back into space, and it can pass right through the atmosphere because the atmosphere is transparent to visible light. But when the ice melts, it usually leaves like something darker behind it, right? Like land, right? Or ground. And so now with the ice gone and with the whiteness gone, now you don't have that same reflectivity. So the albedo has effectively decreased. And what was the Earth's albedo currently?
0.3.
0.3, right. And so if now it lowers, like say it becomes 0.29 or 0.25, that's going to mean that more energy is coming into the planet. Because remember, it's solar constant times 1 minus the albedo. So if the albedo decreases, you're going to have more of that solar energy. So because you have more of that solar energy, that's going to lead to an increase in temperature. That increase in temperature is going to cause more ice to melt. As more ice melts, your albedo decreases. And when your albedo decreases, the temperature increases and more ice melts, and you get into this feedback loop. And so that's pretty important. It's called the ice albedo feedback. And it's something that you should definitely know about. But it's actually not the most important feedback, at least for the short term. Another feedback that we all really need to take into account is what's called the water vapor feedback, okay? And this goes back to some basic physics and chemistry. We all know that water can evaporate, and that can go into the air, so we have water vapor into the air, right? If you leave a glass of water out, eventually it will evaporate. Where did all the water go? It went into the air. That's what makes things humid, right? The more water vapor you have in the air, the more humid things are. Well, it turns out that the amount of water vapor that the air can hold, it's going to reach a saturation point. At some point, the air isn't going to be able to hold any more water vapor, and if you try to put more water in it, it will just come out of the atmosphere in the form of droplets. And the amount of water that can be held in the air, of water vapor that can be held in the air, actually depends on temperature. So at 22 degrees, which is about 72 degrees Fahrenheit, so kind of close to room temperature, right? Air can hold about 19 grams of water vapor for every cubic meter. At 37.8 or 100 degrees Fahrenheit, the air can hold about 51 grams of water vapor per cubic meter. So that's more than double the amount of water molecules that can be held in the air just because you've changed the temperature about 15 degrees Celsius. Okay, so the warmer the air, the more water vapor can be dissolved into the air. Why do you think that would be important? Why would that be important? If there's more water vapor in the air?
It was, I think it will need more energy for radiation.
Right, which was our most powerful out of all the greenhouse gases? Which was the most powerful of the greenhouse gases?
It's the water vapor.
Yeah, it was water vapor. Remember, it wasn't CO2. We had talked about CO2.
Yes.
We've talked about CO2 a lot, but really, it's not the CO2 that absorbs the most. I'm going to see if I can find that PowerPoint that's got black body radiation in it. Let's see. One second. Oh, these climate models. No, that's not it. Again, our carbon cycle here. So we talked about CO2, water in the air, in the atmosphere, as being a greenhouse gas. And then when I showed you this plot here, comparisons with other gases, you can see that in the infrared range, which is going to be about 0.8 all the way, up to larger wavelengths, you can see that water vapor absorbs light in these regions far better than carbon dioxide does. So water vapor is a much stronger greenhouse gas. And so what that means is, if you have some initial radiative forcing and the temperature increases, now the humidity of the atmosphere is going to increase. When the humidity of the atmosphere increases, that's going to be like increasing N, like adding layers to the atmosphere, because now we have more stuff that can absorb into the atmosphere. And we know that increases temperature. And so here again, we have a loop. We have initial radiative forcing, the temperature increases. That means that the amount of water vapor increases in the atmosphere. That in turn increases N, which causes that, it absorbs more infrared and reflects it back to the surface, which increases the temperature, which now causes an increase in the amount of of water vapor that can be in the atmosphere, which then increases how much infrared it can reflect back to the surface. And the cycle continues round and round and round and round again. It also has, some other effects that are worth mentioning. Not only is the air more humid, and that's actually going to be a problem, for humans. If it gets too warm out and the air is too humid, perspiration doesn't work anymore to cool off the body. And so you can overheat a lot easier in very humid weather. But it also means if there's more water in the atmosphere, more water vapor, that's going to necessarily mean you're going to have more precipitation during rain events. Because remember, all the rain is you've got water vapor in the air that's at a certain temperature. Usually warmer means a lot more water. And then some cold breeze comes by, lowers the temperature of the air. It can no longer hold that much water, so the water falls out in the form of rain and precipitation. That's why we get rain. So we would expect to get a lot more rain or precipitation during rain events because of this increased water vapor in the air. We know that with higher temperature, oceans would tend to evaporate faster, and that's going to help get that vapor in the air. And what it looks like is that the wet regions are going to become wetter, because those are the regions in our climate that tend to dump the water out, right? And then there are regions which tend to suck up the water because of the conditions on the ground, deserts, arid regions. And its efficiency at being able to suck up moisture is going to be greatened with increased heat because there's more room to stick the water in. And so that means that it's not going to mean that precipitation increases everywhere. It's going to make the weather more extreme. So, for example, here's a picture. This is from a climate model, okay? And it's trying to show the change in total precipitation by region from the 1981 to 2000 time period to 2081 to 2100 time period, okay? And so they did a lot of modeling on this, and what they're trying to show is this again is like a showing a difference, right? What do we call that when you show the difference in temperature, not the actual temperature?
Anomalies.
Anomalies, right? So this is the precipitation anomaly, right? Here's our precipitation anomaly. And one of the things you'll notice is it's not evenly spread out. One of the zones that's going to get it is in this zone right over here. You can see it's heavily blue. It's probably the largest in this anomaly. And this right now, or this region of the planet is called the intertropical convergence zone. Hold on a second. I'm getting some feedback here. I'm going to stop that for just a second. Okay. So this is called the intertropical convergence zone. Already, it is the rainiest part on the planet. That part of the planet is where a lot of different forces come together, and that tends to be where we dump a lot of rain. It rains there the most. In some places in that region, it's almost constantly raining. And so we dump a lot of water there. Well, what our models predict is that's just going to get more extreme. We're going to dump way more water there, about 60% more water by 2081 to 2090. And so that's a huge amount. But you'll notice also that there are some regions which are going to get drier. And it turns out these regions are already pretty dry to begin with. Okay. So again, we're going to expect, dry regions like the US Southwest or the Mediterranean or parts of Africa will get drier. Same thing with parts of Australia, as you can see here. Way back in the day, they used to call all of this global warming. In the 80s, when they were talking about climate change, the term was just global warming. And they went away from that because really what the predictions show us is, yes, the world is warming, but more importantly, the way it's going to affect climate isn't that every place on the map is going to necessarily get a lot warmer. It's going to really make the climate more extreme in places. There'll be differences, so the climate will change. Okay. So we've talked about the ice albedo feedback, the water vapor feedback. There's also the cloud feedback, which is really important. And this one is both negative and positive. It's got some components of both. So in response to a radiative forcing, we're seeing temperature increase. When you get a temperature increase, you're going to have more water vapor in the air. That's going to lead to more clouds forming. Okay. Now, that can have two separate effects. When more clouds form, remember they're white and billowy, that means they're going to reflect some of the visible light coming in from space, from the sun, is going to be reflected out. So it'll actually increase the albedo, right? And if we increase the albedo, reflect more energy out into space, that should lead to a temperature decrease. So that would be a negative feedback, right? But it's also true that as more clouds form, they reflect more infrared, because remember, they're water vapor. So they reflect more infrared back to the surface because they absorb in the infrared. So it's like adding a layer to the atmosphere. So that would tend to increase temperature. And this is probably the one that we know about, the least, in terms of, we know there's a negative aspect to it and a positive aspect. One that would lead to a temperature decrease and one that would lead to a temperature increase. And at least from the current literature right now, it looks like at the time, at our present time, it's helping keep things cool, but that it may turn positive depending, when it passes a certain threshold and you get more of this infrared. But it's the one probably that we're the least sure about. Okay. Now, the feedbacks we've talked about so far, the feedbacks we've talked about so far are all short-term feedbacks. These are things that we're going to see in a relatively short period of time in the next century or so. There are other ones that have longer time spans, okay? For example, there's something called the permafrost feedback. And this is the one that's probably the scariest and most worrisome. Out of all the feedbacks, it's the one that keeps me up at night. So again, it works like a feedback loop. You have some initial radiative forcing, which increases the temperature. And we know ice melts as the temperature goes on. Well, in Antarctica, we have a huge continent. And this continent, I don't know if you've ever seen pictures of Pangea before. That's the time when all the continents were in one big supercontinent, and continents have since split apart and moved considerably. Well, for a long time, the continent that's now Antarctica used to be closer to the equator. It had lots of plants and animals, probably dinosaurs, all sorts of things, filled with life. But over millions of years, it has moved and slowly sunk to the South Pole and started to freeze over. Well, much of that plant life has just frozen, and even animal life has just frozen in place. And because of the extreme cold temperatures, bacteria hasn't, and fungi haven't broken down the plant and animal matter. And so that's still frozen in what we call the permafrost. We call it permafrost because it's permanently frozen and it stays frozen. It doesn't warm up during the summer or anything like that, or melt during the summer. So there's no time at which that organic matter gets a chance to decay. Well, if the temperature of the planet increases and the permafrost starts to melt, the organic matter that's there will begin to decay again. And whenever you, just like as part of our carbon cycle, whenever you decay organic matter, organisms, bacteria, fungi will turn that into, use it up as food, and then turn that into CO2 and methane, which is then released into the atmosphere. When you release that CO2 and methane into the atmosphere, that again is going to increase our N in our favorite equation, and that's going to increase temperature. And with the more increased temperature, we get more of the permafrost melting and more organic matter decaying, pumping more CO2 into the atmosphere, and the cycle continues. And the worry here is the amount of CO2 and methane that can be released because of the large amounts of organic matter that's frozen there would probably be more CO2 than we've ever put in our atmosphere. Like, think about that for a moment. Huge amounts of CO2 and methane that this continent will just release, way more than we've ever done. If we stop, it's possible for us to stop increasing the amount of CO2 that we're putting in the air right now. We can stop burning fossil fuels, and keep it at the levels that it's at in the carbon cycle. But already there are signs that the permafrost is beginning to melt. And this is really troublesome because as it starts to melt and release more CO2, it won't matter if we stop putting CO2 into the atmosphere, because that continent, once it starts melting, will do it for us. And then there is no stopping climate change. It will just become runaway climate change, and there's nothing we can do about it. The amounts are just so large, it would be hard to pull those amounts of carbon out of the atmosphere, or very expensive. So this permafrost feedback is especially worrisome, but it's a longer term feedback. And because it's never happened before, we don't have great measurements on it. But one thing that should be noted is that, when we talk about these feedbacks, it's really easy to kind of incorrectly think that, once you get a feedback, it's just going to permanently loop and cycle and cycle. And so you'll get an infinite temperature increase from a small radiative forcing, because it increases the temperature a little bit, and then that's magnified by these feedback loops. But that's not what happens, okay? With each trip through the feedback loop, you get a little bit less warming. And you go through it again, you get a little bit less warming. And you go through it again, you get a little bit less warming. So it doesn't exponentially increase it, except maybe the permafrost one. That's a different story. But for all these others, small changes will produce an effect, but they don't go out to infinity. Okay. And so where does this lead us all? So what are your thoughts about this so far? I'm just curious.
I was thinking, essentially, it has climate change gotten so far? Of course, through natural means and human means, has it gotten so far already to the point where the permafrost has begun to melt? Well, not completely melt, but has begun to melt to an extent where, is it at the point now where methane being released from the land masses, is it already kind of seeping into the atmosphere, the CO2?
So some of our latest measurements indicate that is the case, that we're starting to see some methane and some CO2 coming from the permafrost. And that's been out like in the last 6 months, we're starting to see some of that data. So it's relatively new.
Okay.
So one could hope that it's kind of we have time to stop things from getting worse. Because remember, the cycles don't cycle infinitely. Get a little bit, you get a little bit more. Hopefully, we don't get entire melting of the permafrost. But it's certainly worrisome. Other thoughts before I continue? Sorry. Nothing else? Okay, I'll go ahead and continue then. So where are we now? Let me go back to sharing screen. Okay, so we saw with no feedback sensitivity, we would expect that if you doubled the amount of CO2 in the atmosphere, you'd get about 1.1 degree Kelvin in warming, or degrees Celsius. It's the same thing, right? So you'd get 1.1 degree difference. Based on what we see with each of these different feedbacks, our scientists calculate that doubling CO2 because of these feedbacks are going to actually increase temperature anywhere between 2.5 to 4 degrees Kelvin or Celsius. And so our best estimate at this point is about 3 degrees. So doubling CO2 will probably increase temperature by about 3 degrees. And this is really important to know. One, you should know these numbers, right? The 1.1, that's without feedbacks, and with feedbacks, it's around 3. And that's really, really interesting, because note that only 1/3 of the warming that we experience actually comes directly due to the greenhouse gases. The other 2/3 of the warming come from these feedback loops. And so that's why it's really important. You have to consider the feedbacks in order to really understand climate change, okay? And you can't really discuss climate change and mitigating climate change unless you understand climate change in context of these feedback loops that are really, really important. And so let's see, I think I have a list of them over here. The ice albedo, the water vapor, the cloud feedback, and the permafrost feedback. You know, yeah, that's probably the biggest ones. There may be one or two that I'm missing. I don't think so, but I'll look through. Certainly read the chapter that we're currently on. And so the chapter that we're currently on is at chapter 6 in the book, and I'll go into these a lot more detail. But these feedbacks are really, really essential. And then because of how they work, like for example, the water vapor feedback, you know, it really tells us a lot about what our changing world is going to look like. And, you know, why we get some of these more extreme weather events that we see, that we're seeing now already, whether it's the increased intensity of hurricanes or increased amounts of precipitation. We're getting lots more flooding, as you all know. Some of you are experiencing more flooding. Dr. Farusa on Friday is going to be talking about some of these other impacts, direct impacts of what's happening to the world, you know, as we heat it. And much of the rest of the course is going to be delving in and looking at some of those other impacts that are so devastating. You know, it's interesting to note that, you know, when you're talking about like rain events, a lot of these predictions say climate change has already increased precipitation by about 20%. Okay, and so what does that mean? Well, for like a hurricane event or a major flooding event where there's a lot of rain coming down, the first few inches of rain isn't the problem. So if a place normally gets, you know, an inch of rain, the terrain is built to handle that. It's once you reach some kind of a pinnacle, some kind of a pressure point, where now the land becomes saturated with the water. Now every inch after that causes a lot more damage, because now you're getting the flooding and such. You know, up to a certain point, the planet can adapt and the region can adapt. Once you go beyond that point, all that additional is doing more damage to human structures, to people, whatnot. And so when you talk about adding on to the strength of a storm by 20%, the amount of water, that whole extra 20% is doing damage, right? It's not like it's only doing, the storm is only doing 20% additional more damage because of climate change. No, all of the climate change stuff, that's all additional damage. So it's something to think about. I'm certainly interested to hear any of your reactions or thoughts on any of this. I think I'm done with the lecture for now. We got a couple minutes. So if there's any comments or questions, I'm happy to hear them. Looks good. Okay, are you guys enjoying the course? Are we doing okay?
Yeah, we are doing okay. It's just interesting how the course really goes deep. It is deep, like deeper than I thought. And there is small little things that we used to take for granted, like water vapor. We wouldn't know how it would contribute to something as big as global warming. I'm interested, and yeah, I missed much of the class because of my connection, but I what was happening in class.
Well, I'll make sure to post these on YouTube as well, so you can rewatch, and they're also on Moodle. That should be up in about an hour or so.
Thank you so much.
Thanks, everyone. Have a great day.
Thank
And
you.
I'll
Have a
see
great.
you on Friday. Try to make it Friday for our guest speaker. Okay, bye-bye.
Yeah.
Thank you.
Thank you.